Okay, welcome everyone. I'll share my screen in a second. I just want to say in advance, I'll apologize for having the microphone right up against my mouth. I've been sick the last couple of weeks, so my voice has been
It's
giving
okay.
out. So hopefully uh, it'll last for the full hour. It's been an interesting morning. Today, just before the started getting ready for the talk, the hard drive on the desktop PC crashed. So we had a
Wow.
little emergency run down to the computer store today and got ourselves a new SSD. So that's in there now. So hopefully the demos will run relatively smoothly. Let's
Awesome.
share my screen and we'll get into it. So this is how you get in touch with me. To be with the cool kids, I've even got a little QR code you can scan there. But if you want just casual tech conversation, hit me up on Twitter. That's fine. If you like your content in more longer form, you can just grab me on my blog. Or if you prefer video format, I started a tech channel a few years back, and now I've got about 500 videos, mainly how-tos, on my YouTube channel as well. So whatever your preferred mechanism is for content, hopefully I've got something there that you'll find useful. I didn't put it on there, but I've also got a podcast which I started this year. So if you search for The Spoken Nerd, you'll find my podcast on, as all the podcasters say, wherever you get your podcasts. So Apple, Amazon, etc., etc. Okay, let's get started. In terms of bio, this is pretty much what I do most of the day. I look after the asktom.oracle.com website. Done that since about 2015. Most people are obviously very much aware of that. Something that maybe some people aren't aware of is a thing we have called office hours. Probably 2 or 3 years ago now, we realized that there's a whole lot of experts inside Oracle who don't get the luxury of what I do, which is talking to outside customers. They're inward facing experts. And we thought, how can we get customers access to these people? And so a lot of these experts now host a monthly call on their particular topic. And because we have a lot of product managers inside Oracle, we end up with about 2 to 3 of these per week. So there's one on Optimizer, one on SQL, one on DBA, one on Oracle Text, one on language, etc. So all the potential topics, hopefully that you're interested in, there's generally an office hours out there for you. We record all the sessions, so if you click on the videos tab on asktom.oracle.com, you'll see nearly 600 pre-recorded office hours sessions, all of which are there. Don't have to sign in, don't have to register. It's just a matter of free content for you to help you be more successful with the Oracle database. If out of all those 600 videos you can't find something specific that you need for your IT department, reach out to us. We're happy to do a dedicated customer-focused office hours session as well, effectively getting the right experts to talk to you directly on the topics that you need help with. So today we're going to talk about my rulebook of physical design. And the reason I wanted to go back to what you might be thinking is maybe an introductory level talk is that it seems to become a forgotten element. Generally what happens now is sometimes we do data modeling, even that's sort of disappearing, which I'm sure will be upsetting Helly, our previous speaker. But even if we do have data modeling, people are generally taking the data model straight into a physical model and off we go. So before we begin, though, I will have my one little community message, which is as nice as it is to be talking to you, a new user group that I haven't spoken to before, the reality is I would much rather have actually been there. So please follow your local guidelines, follow your local laws. Let's get ourselves all vaccinated so our communities can be back face to face soon. That I would love. I really miss meeting people face to face and the appropriate networking that comes with it. The reason physical design is so important nowadays is no matter how complicated your application, and let's face it, application stacks are getting more and more complicated, deep down in the very belly of all those layers is the database. And so unless the database is running well, then everything else will suffer as well. But here's why people aren't doing a lot of design. Here's a picture of me walking my dog, Bailey. You may hear some barking and chewing in the background. That's him over. I've given him something to eat to keep him occupied for the next hour. And what will happen is, this is how we are as IT developers. You'll be out doing something unrelated to tech and you'll have some light bulb moment, some great idea for a new, for example, application, a new startup company. This is how a lot of great companies and startups were commenced. Someone had a light bulb moment out doing something non-tech related. The problem that has always been the case is if you have this idea in January, and then you sit down and you go through business requirements and all this kind of stuff and data modeling and all these things, normally, by the end of the year, you might have actually something ready to go. That might have been fine in years gone past, but nowadays the moment between you have the idea and the moment that idea comes to fruition is all basically lost opportunity, because there's a very good chance someone else will have that idea before you, or by the time you actually get ready to do it, you've lost your funding, you've lost your budget, etc. So we've had this strong focus for the last couple of decades now, probably the last decade in particular, to try shrink that window between when you first have an idea and first can go live with an application. And the problem is, when you've just got an idea, you haven't got all the all the nuts and bolts, all the details actually fleshed out yet. Really, you just want to have your website up. You just want to get your website up and perhaps put some teasers on there like it's coming soon and that you can register now. Because it's just in its infancy, there's nothing really going on behind the scenes yet, maybe just capturing some user details. Really, the number of lines of code you would like to use to implement that should be zero. That's really what you want to do. You don't want to waste time building a massive application for an idea that may not go anywhere or someone may steal from you. So what you really need in those early times nowadays, in terms to get something up and running really fast, is just some persistence, just the ability to store data that you might be able to use later when your application becomes a bit more fleshed out and a bit more real. And for that, the perfect facility is JSON. And this is why NoSQL databases have become so popular over the last few years, although people are generally starting to steer clear of them now because of the complexities involved. But the ability just to effectively dump information into a data store, not really knowing yet what you would do with it, is still a very, very useful thing to do when you're in startup mode, just trying to get that idea up and running. And the reality of that is, to the number of lines of code you need to effectively store JSON in the Oracle database, well, it's pretty much 3. It's those ones there. You simply open a collection, create a document, and insert and return it back to you. That's one of the cool things with some of the services we offer on our cloud, and don't get me wrong, other vendors do the same, but really the ability to actually grab a JSON document and get it stored somewhere safe can be done in almost 0 lines of code. One of the cool things that we would like to claim makes us different to others is, of course, with us, you can do it for free. And with our autonomous JSON database, you can literally say, okay, I don't know if this idea is going anywhere yet, but if it is, I'm just going to start off with a free allocation of space, have a JSON database, autonomous, all backed up for me, it's free, and I just have a simple API to get the data in. Hopefully, like most ideas, we want these ideas to be successful ones. And one of the cool things with JSON, while those ideas are being fleshed out, is if you want to change your website, so I might have added a survey to it, I might have, for example, now got a beta version of my application. It's still not ready for the level of rigor of a full database, but I might need to evolve the data that I'm storing. And JSON's great for that. I can take existing JSON and simply start adding attributes as they come along. So on this point, I can see, yes, as I've added information about a survey now, I can take customer preferences, I can take their email addresses. It's very, very easy to morph the application because it's so fluid in these early stages just by storing stuff as JSON. And the cool thing is, even though it's all just stored as JSON, one of probably the differentiators of our database over other document databases is it's so easy to take that JSON data and still bring it out as if it was relational data. We've got the JSON table and other JSON transforms that let you view JSON data as if it was relational, which is great for doing things like reporting, aggregations, etc. So as your application is starting to sort of get a little bit more firmer toward its real product, you can still have that JSON storage and then move it toward a relational theory. Hopefully, after maybe that first couple of weeks of just storing information and you've got some excited customers now thinking, yes, we want to actually do things, you might actually launch this first version of your application. And here's where things start to get a bit interesting. Whereas before you've been very relaxed, very fluid, just like whatever information we want to grab, we'll just store. Once you start taking people's money, well, things are a bit more serious there. Now, I'm not saying that a JSON database can't be used for that, but the general principles behind of just grabbing information and storing it as simply and quickly as possible generally lacks some of the rigor that we might want to instill on our data once we actually have people's money involved, because obviously we need the importance of data quality, data integrity, obviously security as well. All those things become that much more important once you actually have people's money on your databases. So that's where we start getting into maybe looking at morphing from, say, a JSON structure into a relational structure. The problem is that's a big jump. Whereas before I was just storing a piece of JSON, now I've got some DDL for a customers table. I've got a products table. I've got some orders. I've got order items, etc. I'm starting to add a lot of code here, a lot of DDL, and a lot of structure. That structure is good in terms of making sure the data integrity and quality is there, but that's a big jump from 3 lines of code to having to design all that DDL and make sure it's correct and make sure the keys are correct, etc. That's a big chunk. And that's why people say, they go, maybe we just won't do that. Maybe we'll just stay with the JSON stuff and see if we can gamble with people's money that way. One of the cool things that a lot of people are unaware of is we have a facility called QuickSQL, and you can get to it from quicksql.oracle.com, which lets you take effectively a JSON look or maybe a document-based mindset and very easily convert that to the relational structures that you want to get that extra rigor. So the cool thing with QuickSQL is you pretty much start to type in a shorthand, and the way the hierarchy is structured, simply by the way you indent, defines things like tables, child tables, foreign key relationships, the attributes, etc. So a sort of structure that looks something like that in QuickSQL, when you hit the generate button, it gives you all the various bits and pieces that you're interested in, and it takes care of a lot of the stuff that you would often not want to bother about yourself. It's going to give you the surrogate keys. It's going to give you the various attributes you want to track rows, who created it, when it was last changed, etc. It gives you all that stuff by default. One second. Excuse me. So I'm going to say our starting model here, once we get from JSON into a relational database, will be this. This has come out of QuickSQL. We've got our customers table, some product categories, products table, and our orders table, and I think our order items table. And if we flick back and forth through this, you can see that QuickSQL's done a really good job here. It's come up with some keys for us. It's come up with primary keys. It's come up with check constraints. It's come up with foreign keys relations. In fact, I forgot that. Yeah, it even came up with the relationships between the tables as well. So in terms of just typing in some keywords and some attributes, QuickSQL gives us a really good starting model with all the keys and quality we expect from the relational database. And I want to stress, this is a good starting model, and it's probably going to be fine for the vast majority of applications you would probably need to write for applications that are going to be able to scale reasonably well. The danger is, just because you have a good starting model, it's very easy to start this downward spiral into things that are going to jeopardize the quality of that model as business requirements come along. For example, people say, I don't just want surrogate keys, I want them automatically populated. And people say, we want audit controls, which means, for example, I want to be able to capture every time someone changed a row, when it was changed, etc. All those kind of things are really superfluous to business requirements, but we still demand them, our customers demand them. So what happens? As I said, this database is the model as its starting point is probably just fine for the vast majority of applications out there. But this talk is really about what happens if your application goes absolutely nuts and is a runaway success. This is one of those classic examples when people say, oh no, that's why we had to ditch Oracle. That's why we had to ditch SQL Server. That's why we had to ditch Postgres. Because as we all know, relational databases don't scale. And as I put, you'll see it on blog sites. You'll see, I'm always amazed at the amount of large customers that you see out there, large data customers who say, yes, we started with a relational database, and then because we got to this many transactions per second, we ditched it all and rewrote the whole thing using Mongo or some sort of sharded database, etc. Which always blows my mind, because often the figures they're talking about are nowhere even near the capacity of what a database can do. So I'm hoping to prove you that this is all incorrect. So let's start with a demo now. Let's do some real code stuff of effectively our starting database model. We'll walk through it in the code, and then we'll see what kind of performance we can get from it. Make sure my typing's okay. So I'm hoping that font's big enough for everyone to see. And all this is a real running of the script of the same DDL that pretty much came out of QuickSQL. So the first thing, I've got my customers table, and I've got a unique, primary key and a unique key, product categories table. I've got my products table. I'm looking like this because my webcam's in front of the screen. I've got my orders table, primary keys, etc. Indexes as required to satisfy the foreign keys, add all the foreign keys in. And because we want automatic surrogate keys, we're going to create some sequences as well. As we know, if we want to populate some of these keys or track when people have changed data, we often do that with triggers. We don't do it in the application itself. So I've got a trigger here that populates customer seek.next file such that if they don't provide a surrogate key, we'll use it, when who created the rows, etc. The same thing for the other tables as well. So we've got some triggers here to capture all that important metadata and populate our surrogate keys. Now I'm going to create some sample data here. This is to seed the application such that we can actually run a benchmark against it. So I've got 5,000 customers, 20 product categories, and 1,000 products. So those customers are going to come into our application and actually benchmark and stress our system. Now, here's my application as such. I've got basically something that creates a new order, a little piece of PL SQL. It's obviously not very complicated. It's just an insert statement. We've got a routine that creates a new customer and a routine that creates new order items for a given order. That's our very complicated application. Now what I'm going to do is I want a means now to actually stress test this application. The way I'm going to do it is I've got a table here called results, and it's going to store information about the benchmarking results that we do, but it's also going to use, it's going to serve a second purpose. I'm going to put some rows in here such that each one of our benchmark programs that runs, we'll try to get a lock on a row in that table. In that way, I can get 5 or 6 benchmark programs all getting ready to slam the system at the same time, but they won't start because they'll be waiting to get a lock on a row in this table. And then when I commit, all the programs will start at once, smash my system, and then we'll see how we go. So I'm using this as a way of also not just capturing results, but in terms of doing effectively some locking to make sure all our benchmark programs start at the same time. And here's our benchmark. It's just a piece of PL SQL. So it's got a couple of routines. It's got a routine called initialization to get all the benchmarking information ready, and then the actual running of the benchmark itself. Now we can see I've got a couple of constants here, which I've hopefully these timings will be about right. It's always tough when Zoom's running to know how much CPU Zoom's taking as well. But you can see how many orders we're going to be placing as a part of our benchmark. And obviously the vast majority of this benchmark is placing orders. But every 200 orders, we're going to assume a new customer joins up and signs up to our application as well. So we're going to be stress testing both the creation of orders and the creation of customers. Here's the actual code. If I scroll back, there's not a lot going on here. The initialization part is just gathering a whole lot of random product IDs, customer IDs, etc. I do this in advance because DBMS random is actually quite expensive. I don't want it to dilute the actual cost of our benchmark. I want to see what the cost is actually just running our application, not collecting DBMS random rows many thousands of times. So I gather them all into a PL SQL table first, and here's our running routine. This is our benchmark. And you can see it simply says for each of the 40,000 iterations, if it's time to add a new customer, we'll put a new customer in, otherwise we'll add a new order. And at the end, we update our results table with some things like how many transactions per second we did, how long the benchmark took, etc. So we're pretty much almost ready to now run the benchmark against our data model. Excuse me. I need to benchmark my throat. As someone said, the package is useful code. Yes, I'll certainly share it. I'll put it on my GitHub repository. Let me just make a note. Remind me to put a link in the chat later. Okay. So to run this benchmark, now I lock my results table. And so what happens now is I'm now going to spire off a whole stack of SQL Plus sessions. You can see them all fire up now. That's why I've shared a large part of my screen. And you can probably see just in the mouse here, there's a lot of windows all running at once, right? But they're all stuck. None of them have started yet because I've locked them. I locked this table first, and then I fired up 6 SQL Plus sessions, all in separate windows. But nothing starts until I hit commit in this main window. So if I hit that and commit, you can actually see these are all now launched into running the benchmark. So 6 of them running, and they're simply can hear my fan going on the PC. They are absolutely smashing my computer, trying to get 40,000 orders in as fast as they can. And that's 6 lots of 40,000 orders. So they're smashing away. I'm making idle chit chat while I hope they finish. And you can see they eventually start finishing. Once they've all finished, they'll automatically disappear. And I come back to that first window again. What does it tell us? It tells us we got finished in about 20 seconds. And I think it finished in about 20 seconds. And we got about 12,000 transactions per second. Now, as I said, that opening model, that's pretty good. I mean, this is a $1,000 desktop PC, and yet I can get 12,000 transactions per second out of it. Just for a point of reference there, Visa at popular times of the year takes about 5,000 transactions per second globally. So 12,000 transactions per second, I admit they're very simple transactions, is still mind-bogglingly impressive on a very cheap piece of hardware. The Oracle database is very, very quick. The other thing I've spat out here is a distribution of where that time was spent. And this is across all 6 little benchmark children that we're actually slamming away. And we can see that about 108 seconds, because we had 6 threads, so it's actually about 17 seconds each. 108 seconds was spent on CPU, about 90% of all the time that was taken to run that benchmark. So that's good, but let's see if we can do better. Now, here's an interesting statement. The aim we want here is actually 100% CPU, not 90% of the time being CPU. Now, that seems a bit strange. I know, because generally when we talk about performance, we're talking about lowering the amount of CPU. But let's remember that CPU is money. That's how it works. Whether you're on premises, you are licensed by the CPU. If you're on cloud, you're licensed predominantly or billed predominantly by the amount of CPU you use. So why would I say the aim is 100% CPU? Because if I flick back to my results, if the CPU utilization across the whole benchmark was 89%, i.e. 89% of the benchmark time was CPU, 11% of the time I couldn't get to use the CPU I have. That's 11% money wasted. Something stopped me from getting access to all of that CPU. 11% was lost somewhere else. That's why the aim is to get to 100% CPU, because it means you're actually getting the best utilization of the resources you have. Once you can get to 100% CPU, don't get me wrong, the aim is to take that 100% and make it a smaller figure. So I might burn 5 minutes of CPU at 100%. If I can get down to 3 minutes of CPU at 100%, that's obviously much better than 5 minutes, but the aim is always to be able to use the CPUs. That's what you're paying for. You don't want to have the CPU sitting there idle because something is stopping them. So remember, when you're performance tuning, the aim is to obviously reduce the response time, but as a general rule, you're trying to get CPU being the more dominant part of the equation, because that's what you'll build for in most cloud vendors. So I got 12,000 transactions per second. About 90% of the elapsed time was burning CPU. I'd like to get that closer to 100 and then also bring it down lower. Can I do better? Well, let's remember that triggers are just like application code. A lot of people think, I've put it in the database, I've put it in a trigger, it's separate from my application. Whilst physically it's separate from your application, it is just code, and code equals CPU. And one of the risks of using triggers extensively in the Oracle database is that it's pretty hard to detect when what portion of code is trigger, or what portion of CPU is trigger CPU. Because if I run an insert that inserts 10,000 lines and that trigger fires 10,000 times, at the end of the exercise, I'll have a total CPU figure for the insert statement, which includes the trigger. It's very hard to piece that apart. But let's have a closer look at our triggers and see why we had to have them. One of the first reasons we had was if you don't have a surrogate key, we need to get it from the sequence.next file. And that's a common technique we've been using for many, many years in Oracle. Also, we had, if the date time was null, we defaulted to sysdate and created by, etc. The problem is the reason we have triggers and we just don't use the default clause is this. If I create a table called T, which has a column where I have a default of N, if I insert a value of 1 for the first column and forget about the second column, like I don't reference status at all, that picks up the default. But just having default of a value doesn't stop me from doing this. If I do if I do insert into T, nominate the explicit column and nominate a value of null, I end up with this. This has always been one of those issues when it comes to wanting to default information. Even if you specify default, if the column is potentially nullable, then you have this issue where people can override it. There's always been that worry that people would somehow sneak a null in or sneak an illegal value into your applications. And the workarounds to handling that are often unpleasant. Sometimes, in years gone by, we would have to actually do something like this: wrap the entire insert around with a procedure call. So every time you do an insert, you can pass in the primary key and the status to this table. If the status is null, you use the word default. I'm not sure if people are familiar with that. If a column has a default, you can actually use the word default to pick up that default value. Otherwise, if it's not null, then insert the p status, etc. However, way back in 12c, we introduced a lot better null control declaratively. Now we can do things like this. We can have default on null, which says even if someone tries to jam a null in there, we will grab the default value as declared. So even in this case, when I insert all nulls for these 4 remaining columns, it doesn't matter. They'll always get those default values. That's very, very useful because it means I don't need to have triggers in all those places that I used to use them to assign defaults and avoid nulls. Armed with this knowledge, let's go back to our demo now and see what benefits we get now that we know that we can maybe do away with some of the triggers. Now, in terms of establishing sort of a convention here, so you can see how the demo differs from the previous one. Anything that's been sort of significantly changed, I put in uppercase. So now we can see in our customers table, because we're going to not use the triggers, we can actually say default on null, and anything which is uppercase used to have a trigger to populate it. Now we're using the declarative information to populate it there like that. Primary key, unique keys are the same. Then we have a product categories table, nothing to do there. Our products table, nothing to do there because that was already there. Here we have our orders table, and now we're taking advantage of the defaults to get the primary keys, the sysdate, the user, etc. The rest is pretty much the same. With this order items, we've got another default in there. And our foreign keys are the same, no changes there. And the best part is all that code I had before about the triggers, it's now all commented out. I don't need that anymore. I don't need any of those triggers on insert. So they can all be commented out. I don't need them anymore. The rest of the demo is now exactly the same. Seed the tables with the same 5,000, 20, and 1,000 rows. There's our application. There's our results table, just like before. Here's our benchmark, which is identical. In this case, I've just gone straight into locking the table. And what I'll do is commit straight away. If I go back to the first, you can see I've committed straight away because we now know that how this benchmark works. So once again, 6 benchmarks running. You can see them chugging away. That's number 2, 3, 4, etc. They're all burning away as fast as they can. Let them finish. They'll all disappear. And here's our results. So what benefit did we get by doing away with the triggers? Remember our first one? Elapsed time was about 20 seconds. We've now dropped down to about 15 seconds elapsed time. And you can see we've got a nice, healthy jump in performance. We've gone from 12,000 transactions per second to 15,000 transactions per second. What's that? That's about 25% with literally no change to the hardware or anything. So the actual performance has improved. We got better transactions per second and the overall elapsed time was reduced, but we seem to have gone a little bit backwards here. What's happened is the triggers were actually holding us back before. Now the triggers are gone, we can actually we're trying to flood the system with more work, and that's introduced more problems in terms of contention. So our CPU overall was down, but now it's only 85% of the total. We'd like it to be 100%. And we start seeing, where some of the bottlenecks might come in. We have this thing called ENQ, SQ contention, buffer busy waits, TX contention on indexes, etc. There's a few bits and pieces in there as well, but let's focus on some of these elements and see, can we do better again? Now, a quick segue I want to talk about audit is one of the things that does come out is, yes, we've turned off all the insert triggers, but people say, what about updates? There's no such thing as default on updates, so I'm still going to have triggers on updates. This is true, but the reality is we often update far less often than we do insert. But if you do have a lot of updates, what are some of the options? People often say to me, I need comprehensive auditing on my tables, not just the last time someone changed it. And really the best way is Golden Gate. If you are really committed and the audit is a business critical operation, really Golden Gate's the best way to do it because it's going to capture absolutely everything very unobtrusively because it's done against the reader logs. However, it's a separately licensed product. You're going to have to pay for that. There's no such thing as a free lunch. For all its awesomeness, you have to pay a fee. One of the things we've all done sometimes to maybe avoid spending that money is this kind of concept when it comes to auditing. For every table in our application called T, customers, employee, etc., we have a partnering table called T audit. And then what we do is we create triggers every time you insert or update or delete on the base table, we stick a row into the audit table. Now that works, but it's really, really slow. It's a trigger that fires on every single row. In fact, we can see that if I try insert 10,000 rows and do a trace, we can see that I've done 10,000, I've only done one insert statement here in my application. It resulted in 10,000 insert statements into my audit table, and it burned a fair bit of CPU, etc. doing it. It costs me a lot. If you're currently doing that kind of approach, there are some other options you might want to consider. One is Flashback Data Archive is a mechanism of mimicking audit with a facility which is actually not really designed for audit purposes. If you've never seen Flashback Data Archive, we create a thing called a Flashback Archive, nominate a table space, and nominate how long you want to hold data for. Then what happens is no matter whatever you do to your table, once you put it in this Flashback Archive, doesn't matter how much DML you do, you can actually query that table as it was at any point in time in the past. So I can say, show me the employee table as it was 3 days ago or last June, for example, any moment in time up to that 1 year in the retention. And you can see the execution plan is digging into these internal tables that get created for you. Of course, people say, how does that relate to auditing? Just because I can see what the employee table looked like 3 months ago, that doesn't give me an audit trail. But one of the cool things with Flashback is we have a thing called a Flashback versions query, this versions between, which gives you every change to every row, insert, update, insert, etc., timestamps, etc., for every single row on the table. Using this versions between query gives you that audit trail without having any triggers. You've simply put the table into a Flashback archive. If you're not happy with that, you have some particular kind of requirements. If you must have triggers, one thing I'd recommend you have a look at is I've written an audit utility. It's just a procedure that generates the triggers and stuff for you to make it as efficient, as optimal as possible. So it gives you all sorts of controls in terms of what you audit, how often you audit, bulk binding on the inserts. It tries to be as efficient and as flexible as possible. So feel free to grab that. That's just off my GitHub repo. Oh, in fact, someone asked the question before about the package, the package for the benchmark. It's not up there yet, but I will put there, but that's my GitHub repository. So github.com/ConnorMCD. That's the end of my audit segue. So we got rid of the triggers. Can we do better? A couple of things we can look at now. Cached sequences are not actually cached. When you do create sequence, it looks like this in the data dictionary. It says, yes, the cache size is 20 by default. And when people see that, the first thing they think is, oh, we've now burnt up 20 bytes of memory in the SGA somewhere. And therefore, they don't want to do something like create sequence cache 1000 because that's going to consume 1,000 pieces of information in the SGA. This is not the case. What happens is when you create a cache, you're simply nominating effectively an upper bound on what information can be obtained from memory. So when I first create a sequence, it says the last number is 1. The sequence has never been used, so the next number will be picked up will be 1, and the cache size is 20. When I do my first select sequence now next value from dual, I get the value of 1, and this last number's been bumped up to 21. So all it's saying is that I can now get the numbers 1 through 21 out of a reference in memory before I have to go back to the cache. A sequence cache looks more like this. It's simply a single entry in memory saying, yes, you can use the numbers 1 through 1,000. And it'll simply record that counter. Someone's used 1, someone's used 2, someone's used 3, up to 1,000. And then we go back and update the data dictionary, etc. So the next value will be that. So it doesn't matter what the cache size is. It doesn't impact memory in any way, shape, or form. All it impacts is what sequence numbers would disappear if your instance went down. So if you have high frequency transactions, you really want to have a high cache to avoid all those trips back to the database or data dictionary to update the sequence values. The second thing I want to talk about is this thing called the myth of foreign key indexes. I'm sure there's a million blogs out there where you've been told every foreign key must have an index. And don't get me wrong, it's probably better to go down that path than to have absolutely no indexes. If you have to choose one or the other, it's probably safest to have an index on every foreign key, but it's not a rule. Here is the guidelines for why you need foreign key indexes. If you mess with the primary key on the parent table, if you update it, if you delete from the parent table, or, for example, or do you get performance benefits by having that index on the child table? That's the only two rules. If you mess with the primary key on the parent, or you need the index like any other index for performance on the child, then you should have a foreign key index. But if you don't, then they're not needed. So for example, let's go back to our data model. I've got customers and orders. Will I delete a customer? Probably not. But then again, I mean, if customer has existing orders, you would never delete them. You'd set some sort of flag saying, they're no longer a valid customer, but you wouldn't delete those orders. But if someone's a new customer, for example, if they might create their record and then have any orders yet, they might be allowed to delete it. So you might delete it. Or if I look at the orders table, it's probably very likely the customer's going to come in and say, show me the orders for me, for my customer ID. So the customer ID column on the orders table will probably need to be indexed anyway. So in that case, we probably need that foreign key index. How about this one, products to order items? Will I delete a product? I would say never, because the moment someone orders a product, it's in your record of financial records. You can no longer delete that product. You would only be able to, for example, update it and say it's no longer available, etc. And it's very unlikely people would say, show me all the order items, which are individual line items for an order, by product. The vast majority of people are going to show me, if they're going to ask for all the order items, they're going to ask to come in by an order ID. So I probably don't need that foreign key index. And these are the decisions you can make on a step-by-step basis. So let's now run a demo knowing that we can increase our sequence cache sizes and do away with some foreign key indexes. So now I'm creating the indexes. I'm not creating too many customers, so I'm doing a cache of 100, orders 5,000. Because I'm doing a lot of orders per second, I'm going to bump that cache up. The rest is pretty much the same, no uppercase here. There's my customers table, there's my products, orders, etc. I'm keeping this index. This was an index we already had. This is the foreign key index we just discussed. We're going to keep that one on customers to orders, but I'm not going to keep this index. As we discussed, we're probably never going to need that because we're never going to delete from the product table. The rest is the same. There's our sample rows. Here's our benchmark package. Now we just get straight into it. We all know the drill now. So they're all running away. We wait for them to finish. I'll have a cough. It's all finished. And suddenly we start seeing the cost of those sequences being updated in the data dictionary. I've gone from 12,000 transactions per second initially to 15,000 transactions per second. Now I'm at 29,000 transactions per second. And we can see our CPU is starting to head up toward that magical 100 mark. So we've eliminated some points of contention. You may remember that one of them You may remember one of them was ENQ SQ contention. That's SQ for sequences. So our big items now are buffer busy waits. Cursor pinning, I'll struggle to get rid of because there's not enough CPUs on this machine to do it. And then we get to things like index contention, etc. But we've gone from 12,000 to almost 29,000. Now, some good news. What I just said about sequences, I lied a little bit about, because from 19.10 onwards, you can almost say we sort of gave up. We said, look, people aren't ever changing the cache sizes on their sequences. They're just leaving it at the default. So we now do it dynamically. In the documentation, I've got a blog post on there as well. You can see that now what happens is if you have any kind of cache on there, then over time, if you start hammering that sequence, we will behind the scenes increase the cache size to avoid sequence contention. So thankfully, you don't have to explicitly set cache sizes now because we just gave up. We said, look, we're going to do it for you. Can we do better than 29,000 transactions per second? Well, because all these surrogate keys are just sequence values, they're just ascending numbers, 1, 2, 3, 4, 5, 6, etc. Now, they can be a bit of a problem. Now, shameless plug, if you want to see some information about ascending keys, go to my podcast, The Spoken Nerd. I do a whole podcast episode on ascending keys and how to deal with them. But we're going to cover that now here. Way back in Oracle, about 8i, I think, when we introduced automatic segment space management, we almost solved the problem of concurrent inserts into tables, because now, as a table gets populated, we scatter the inserts across many, many blocks. I'm not sure how that animation is going to come out over Zoom, but hopefully you get the idea. We just don't start at block number 1 and work our way up and fill it up. We actually grab a selection of blocks and stuff data into multiple ones. It was critical for us to make, or might be 9i, critical for us to make rack scale well across multiple nodes. So inserts to tables get scattered across multiple blocks to avoid block contention. But you really can't do that with an index, because an index, a row has to go in its particular spot, because an index is stored as an ordered structure. And if you think about an ascending key, every single value is higher than the previous one. So every single row goes into that leading block because it's an ordered structure. Now you've got thousands and thousands of rows all competing for this same block in memory, which is that ENQTX contention you saw before. To avoid that, we have a thing called hash partition indexes. And we can actually take an index and ask the database to split that index into multiple physical chunks, which gives us effectively multiple index structures split by a hash key. That's normally never going to be a drama for primary keys, because primary key lookups are always based on equality anyway. No one ever says, show me all the values with a customer ID greater than 17, because 17 is a meaningless number. So now we're scattering that leading blocks. We now have 4 leading blocks or 8 leading blocks, depending on how many partitions we choose. Let's do another demo. So we've got our nice highly cached sequences here. We've got our table as before, our products table as before. Once again, there's stuff that's changed in uppercase. I've got my index. In fact, I actually went the whole hog here. I actually even partitioned my table, mainly so the indexes would be bound to it. I partitioned my table into chunks. I partitioned my index into hash partitions to spread out that load of ascending keys. I did the same thing on my order items. And the rest is the same. So I've done all the seeding. Here's my benchmark. It's all ready to go. And off we go. I think this is our last benchmark. Chugging away. It's done. They'll all disappear. And here we go. Check out this. Remember, we started with a very good data model and we got 12,000 transactions per second. We've got a little guest host here, my dog. From that very first benchmark, we've gone from 12,000 to 31,000 transactions per second. Once again, on a $1,000 PC. Stock standard PC, this is running Oracle 19.12 on Windows. So anyone who wants to bag Windows, you're killing me. So remember the initial elapsed time was 20 seconds. Now I'm getting the work done in 7 seconds. It's 2.5 times faster, plus 2.5 times the transactions per second. And look at my CPU. It's almost 100% CPU. So I'm not losing time anywhere. I'm getting the absolute best utilization of my hardware that I can. Pretty cool. In extreme cases, if you have things that are even stressing, your 20 CPU boxes, It is not unheard of for people in massive cases to actually partition their tables by rack instance ID, therefore giving you linear scalability. My dog keep whacking the table. Linear scalability of multiple rack instance nodes. We've got benchmarks on our autonomous white papers showing literally millions of rows per second simply by doing this kind of partitioning across rack nodes as well. So we've spent a good chunk of our time, what's my dog doing? A good chunk of our time talking about getting data into the database as fast as we can, which is generally the most common thing we do for physical design. But obviously, once you've jammed all that data in, people are going to want to get it out. So let's finish off with a few quick explorations of query performance explorations. In particular, people often say, yes, I believe you in terms of getting data in really fast, but you've just dropped all those indexes. That's going to kill me in terms of querying. So let's look at faster queries with the same indexes that we've just got. Now I'm going to not use our benchmark table, so I'm just going to use an example here of a customer transaction table, a very similar one, to talk about the idea of massaging your data to get best benefit out of indexes. Here's our customer transactions table. It's got a customer ID, a transaction date. It's like one row for every transaction. What I've got here is 1,000 random customers, and what am I putting in here? 10 million rows. So 10 million rows spread across 1,000 random customers. And I'm just using sysdate here to generate random transaction dates. And because customers are going to want to see their transactions, we'll put an index on the customer ID. So here's your typical kind of query. Someone's customer 123 logs on, they say, show me all my transactions. This is what they see, which is obviously not ideal for your customers. Now, why are they seeing that? I put an index on that column. Let's look at the explain plan. It looks fine. I've done a max here such that we don't get all the rows, but it's the same premise here. I'm basically circling through all the rows for customer 123. I did the right thing. I chose an index range scan, but this is what came out. 8,000, almost 9,000 physical reads. Now, why? Why is that so slow? Well, the problem is customers don't act like we'd like them to. Customers all come in at random times and do random orders. So scattered throughout my table is customer, here's a record for customer 123 at 9 a.m., one at 11 a.m., one at next Tuesday, etc. All the different customers are interspersed throughout each other, which means when you're querying by indexing, even though you very quickly get the rows in the index, every single row in that index points to a different block in the database table, which means a physical read. These are some of the things you can do to improve that. If you know that customer ID queries are going to be the pivotal query for you, the most important query for you, from 12.1 and above, you can say, I want my customer trans table to be clustered by linear order on customer ID. This doesn't do anything. It simply nominates some dictionary metadata. It says, if you are loading this table, try sort the data by customer ID or cluster it by customer ID. It's only when you then load the table, or in this case, move it. In this case, on 12.2, I can move it online, so no interruption to service, and that will reshuffle the data without taking it away from people so that the customers are all clumped together. So now my customer data looks like this. All the customer 123 stuff is clumped together in certain blocks, customer 47, and so forth. Now when I'm on the query, I get the exact same explain plan, but now it's 23 physical reads, not 8,000 physical reads, because now customer 123 rows are all co-located. This is something I could do in quiet hours just to reshuffle the data to maximize the benefit of the existing queries. People say, but I'm not on 12.2. Oh, I've got a Q&A here. I'll come back to that, Frank. I'll answer that in a second. I'll just finish off this little section. People say, but I'm not on 12.2. If you're not on 12.2 or you're not on Enterprise Edition, DBMS redefinition can also take care of that for you. It'll do just as good a job. Now, let me answer Frank's question, and then we might wrap it up. Frank has asked, for the benefit of everyone, what about reversed key indexes? Don't they also help with the kind of contention of ascending key contention? Yes, they do. Let me tell you why I'm not a big fan of that. And don't get me wrong, if you don't have a partitioning license, then yes, reverse key indexes would be the next thing to look at there. The reason I'm not a huge fan of reverse key indexes is a B-tree index in theoretical form normally sits at about 67% full. If you simply scatter random rows into a B tree index, it normally sits at about 67% full because every 2 out of 3 times you have to do a split block, and therefore you get about 67% utilization. With ascending keys, because we have an optimization which simply says if an index block is full and the next value is higher than the high watermark, we leave that block full and simply add a new block. Then ascending indexes will actually be almost 99% densely full. That makes them querying and very, very compact. They're very efficient in the buffer cache. But yes, if you're hitting ascending key index contention problems and you don't have a partitioning licenses, then yeah, you just have to sort of cop that less efficiency and use a reverse key index to solve that problem. Okay, how we go? I think I have to flick through a few here. This is just how to use Diminutive redefinition. And there was a thing about talking about indexing as a strategy, but I don't think we have time for that. So we might just have to wrap it up. Let me just.
We have 5 more minutes, so you can just go on.
Yeah, I'll wrap it up because there's someone after me, isn't it? Yeah, I'm going to wrap it up because yeah, nothing worse than being the speaker that runs into the next person's time. And what's more, that's a carrot to have me back in person next year.
Sure, definitely.
So to wrap it up, none of this stuff is sort of rocket science. This really is all just basically stuff that's covered in fundamentals. We didn't do anything sort of undocumented or unsupported, etc. We simply took an existing, very good design. Don't get me wrong, 12,000 transactions per second is more than you'll probably ever need for many applications. But as our demands increased, we showed how we could change the physical design to absolutely smash it out of the park. All those things we talked about today are covered on the standard Oracle documentation. In particular, the concepts guide is fantastic. It talks about how blocks are structured, how to get the best out of them in terms of density, how to avoid contention. And the other one is the application developers guide. These are 2 guides that are probably the one thing that I like best in the Oracle documentation because they're not really reference material. They're more just a set of sort of tutorials and guidance for how to get the best out of the Oracle database from a physical design perspective. And if you can read those 2 back to back, rest assured, you'll be more of an expert than probably most current Oracle people out there, no matter what their level of experience, because no one takes those time to read those 2 excellent references. But as I said, every Oracle database you build doesn't have to have those extremes. But definitely start with good. Start with a good, rigorous relational model. Once you start doing things like taking people's money or their secure data, relational generally is the way to go because of the security, the data integrity, the data quality. 12,000 transactions per second is going to be perfectly fine. But if you know how to get to great, then when you get those what we call success crises, where everyone starts loving your application and loving your database and starts smashing it, you'll be able to respond to give them the scalability needs that they're going to demand. That's me done. I'm sorry we didn't cover everything we could have covered. Lots of more goodies to come, but I hope you enjoy that. Hope you are impressed with the amazing power of the Oracle database. Still blows my mind that a $1,000 PC, don't get me wrong, you got to license it, but a $1,000 PC can get you 30,000 transactions per second on an Oracle database. Still very, very impressive in my book. Let me stop my share. That's how you can touch me on Twitter, on my blog. Hopefully you enjoyed that. If you have any other questions or anything in the chat, feel free to reach out to me now, or obviously just follow me on Twitter. My DMs are always open on Twitter, so you can always ask me questions there, or asktom.oracle.com. Thank you very much for having me, and I'll hand you back to our hosts.